This meeting is being recorded.
In this video from chapter 19 on electrochemistry, we're going to take a look at what are called voltaic cells. And later in this chapter, we'll see something very similar referred to as an electrolytic cell. But the point of this introduction is that voltaic cells, these will be spontaneous reactions. So these setups we're going to see promote the movement of electrons without any outside force, such as electricity. So that's the main difference between a voltaic cell. It will spontaneously have this oxidation reduction reaction occurring, and electrons will be transferred and energy will be released. So that's what we see here, versus the electrolytic or the electrolysis process, where we need to pass an electric current through our cell. So let's take a look at what's happening below here. We have two half reactions right now. We have our oxidation reaction. Remember that losing electrons is oxidation. And then we have our reduction reaction. We see that we're gaining electrons in that reaction, and then we're reducing our copper. So keep that in mind. We see electrons as a product when we're losing them. We see electrons as a reactant when we're gaining them. But it's also good to note that these voltaic cells, they're only going to be spontaneous in one direction. So spontaneous in one direction. We'll see in the next video how we can calculate if they will be spontaneous or not, calculating the cell potential. Some more things to know. What's the electrode? So the electrode, we can see the anode over here. I'm filling in, that's a zinc anode, and then I have a copper anode or cathode over here. These are both electrodes in general. One's an anode, one's a cathode. So these are pieces of metal, strips of metal used to in an electrochemical experiment. So again, in our case, we have solid zinc and solid copper. Zinc is our anode, copper is our cathode. And what we can see at a microscopic level or atomic level here is that the zinc anode, the zinc electrode, will be losing mass. Some of these this zinc metal will be turning into ions, into zinc 2 plus, and we see that in the half reaction down below, this half of the cell here. So what's happening is that the zinc anode is actually going into solution. At the same time, we see over here in this image that the copper ions that were in solution over here, we see copper ions, that bluish color, they're coming out of solution, and this will actually gain mass, this electrode. So after you do type of voltaic cell experiment, you can actually weigh your cathode and it would be heavier. So we see that half reaction down below. So let's review some of these other concepts. Voltaic cells, they use spontaneous reactions to produce electricity. So again, we're only spontaneous in one direction. At the anode, we will see oxidation. So that's why that zinc is going from solid to a charged species to zinc 2 plus ions. And we can remember at the anode, there's oxidation. If we remember our friend, the ox, we have an ox. And then we can remember that reduction occurs at the cathode because we remember our friend, the red cat. So these are just ways, just like Leo and Gur, that you can remember, where we're losing electrons, where we're gaining electrons, which half reaction should be placed with which anode, which electrode, etc. So once we begin to have electrodes flowing, the charge in each beaker would not be balanced, and then the electron flow would stop. So to correct this, we place what's called a salt bridge. So this term here, it's this U-shaped device, this thing that we see actually up here in this image. So this is our salt bridge, and what this does is that it moves cations towards our cathode. So that's what we see here, these sodium ions. And then we have nitrate ions, anions, moving towards our anode. So this restores the charge in our solutions. This keeps the charges balanced. And then we continuously see this flow of electrons. So electron flow can continue if we have this salt bridge. Another form of voltaic cell that you might see is with this semi-permeable membrane here, where anions and cations can flow freely through this porous barrier. So you need either the porous barrier or a salt bridge to keep the charge neutralized, to keep the charge constant and then balanced, and then we can see that flow of electrons. So we should note the direction of flow. Electrons will leave the anode. So they'll leave the anode and they'll flow through a wire towards the cathode. So they start at the anode, they go to the cathode. The cations formed will dissolve in solution in the anode compartment at this point. So after electrons had left our zinc anode up above, we see now zinc cations in our solution. Then electrons are taken by the cation, and we see that neutral metal is deposited on the cathode. So this will be referring to our copper 2+. We add some electrons, and then we get copper solid on our cathode. So that's the setup and the general form that you're going to see of these voltaic cells. So the reason that these can be utilized is that we create this potential, this cell potential, between the different electrodes, between the anode and cathode. And this is referred to as voltage, this potential. It's also called the electromotive force, which refers to the motion or movement of electrons. So we can think of our anode up here as the starting point of electrons. So that would be the top of this waterfall here. So what we're showing is the potential energy. The direction of flow of water is from the anode to my theoretical cathode down here, where we have very low potential energy. So we start with high potential energy at the anode. Electrons will be moving in this direction towards the cathode, and then we have that low potential energy. So this is referred to as the cell potential, and it is abbreviated as the E of the cell. So the energy of the cell, the potential of the cell. And we can also think of this electron flow kind of like a push or a movement of electrons in one direction. So we see them begin to flow spontaneously when we have a certain setup, a certain anode and certain cathode, certain electrolytic solutions. We'll see this redox reaction start, and it always moves from higher to lower potential energy. One other thing that we should note before we do any calculations or any cell notation examples, cell potential is measured in volts. And we can equate 1 volt to 1 joule, so a unit of energy, per coulomb. That's what that C is below there. So we'll see this equivalent value shown in some calculations later on, where we have to relate volts to joules and coulombs. And we'll continue in the next video with cell diagrams and our next sample exercise.